Good morning, Dr. Terrell.
Ah, it was Cindy making noise.
Sorry, got a little far from my laptop with the headset.
Really? Oh, that was all it was, huh?
Yeah, went to get some water.
Well, that's okay.
I'm
That
back.
is good. We all must drink water. We all must drink water. So let's see. Good morning, Casey. How are you doing, my
Morning.
dear? Ah, er, there I go. Chopping off my head, focusing on my big belly. There we go. Ah, nothing good to see here. Okay, so what shall we do today? I have a suggestion. Let us, good morning, Diane. Let us talk about, analytical separations. And to do so, I will share a screen. Yes, I will. Very novel approach here. So I'm just gonna put you guys up here so I can see you too. Okay, so actually I should put you down near my camera. So when I'm talking to you, I'm looking at you, right? There we go. So now I can look almost directly at Cindy and at Casey, who are like one on top of the other. And then if I'm looking up off to the side here, that means I'm looking at my notes. So anyway, so the chapter starts with description of solvent extraction, which is really interesting, but we will not cover. It's basically, I don't want to throw a bunch more algebra at you, because that shit just makes me nervous. And I do not want anybody to not get chromatography because we started with extraction and there was a bunch of math. So we'll go straight into chromatography, and then we'll just talk about some topics in chromatography which are important, right? So what is chromatography? Well, we can give an example of that by looking at the idea of breast milk. And what breast milk is a very complex mixture, and has obviously water, lipids, carbohydrates, proteins, and various vitamins and things. And so there's there's all kinds of different ways to analyze breast milk. For example, you do lipidomics, is the study of all the lipids in milk, or proteomics is the study of all the proteins, or you could you could target a particular protein or lipid or carbohydrate or something like that, right? And there's when you want to analyze breast milk, basically you're doing three things: you're extracting, you're separating, and you're identifying and quantifying each lipid, and or each, if you want to do lipidomics, you're identifying and quantifying each lipid, right? And here is an LCMS of lipids in I presume human breast milk, human breast milk. And this is a pretty impressive, gosh darn. I'm almost thinking this could be a GC mass spec because it's got so many very sharp peaks. But unfortunately, they don't specify, but it's not really here or there, but these are all the lipids that you find in breast milk, and vitamin A, cholesterol, vitamin E, and then heavier lipids, which are they're lipid-derived proteins and things of that nature, and each of them produces a distinct peak in the chromatogram, and what we're looking here is detector response, which is, in this case, it's summed over all masses, right? Because the detector in a GC-MS is itself a mass spectrometer. So this is two types of separation. One is by essentially boiling point along the time axis. Then at every time point, there's another separation that's affected, which is along the mass to charge ratio of the currently eluting species. So it is a pretty cool and high resolution thing. So now we're going to skip over solvent extraction and go straight to what is chromatography here. And in chromatography, one of the common things you always have is a stationary and a mobile phase. So, I don't really quite know how to emphasize, this fact, but, it's the separation is based on the motion of things, motion of chemicals down a tube. And the mobile phase is either a liquid or a gas. I don't think that there's any kind of plasma, if that's really another state of matter, but there's a liquid or a gas that moves through a tube, a column. And then there's a stationary phase, which is, it's bonded to the column normally, or it stays placed inside the column. And in this case, a viscous liquid can be bonded to the column, or you could take solid silica particles and coat their surface with this viscous liquid. And so essentially what happens is, I think you've probably most all seen or experienced something like a column chromatograph here, where you have a column. This example here is intended to portray a large separation. A separation involving say 100 milligrams of solute and then there's probably maybe 1, 2, maybe 300 grams of hydrated or solvated silica here in the column. There's a porous disc in the bottom, which prevents the silica from flowing past. Then there's, typically there's some sand or something up on the top. And then you dissolve your solutes and you pipette them in the top. And then you start introducing fresh solvent, fresh solvent or eluent down the top. And then that will simply carry these molecules down through the column. And the idea here is that any molecule with stronger, i.e. more permanent interactions or less impermanent interactions with the column will be retained more. So, the first to elute or emerge is the solute that's more soluble in the solvent. And the later one to emerge is the less soluble. So so this is pretty horrifyingly bad, but they used to use calcium carbonate and calcium hydroxide and other stuff like that, and they would dissolve things in hexane, or God knows what they used it in those days, some sort of petroleum ether, and they would flow these down these highly polar columns, and things would separate, but it's a very, very low resolution sort of separation. And oh my gosh, I just learned a word. Eluate. Oh my God. Eluent and eluate. Holy snap and arseles. All right. I've been a practicing analytical chemist for like almost 30 years. And I've never heard anyone ever say eluate. But now here it is in a stupid undergraduate textbook. Okay. So we can do adsorption, partition, ion exchange, size exclusion, or affinity chromatography. These are different mechanisms by which molecules interact with the stationary phase and are retained. In adsorption, which is very commonly practiced as flash chromatography, it's like jump and jack flash, right? And their flash is very well cemented in the chemistry lexicon. And there are commercial instruments now called combi flashes, which and combi flashes use large columns, and generally this type of chromatography uses silica as a stationary phase, right? And then some nonpolar solvent. And nobody fucking does it with gas, so shut up, idiots. Liquid is going to be hexane, methanol, ether, and other nonpolar solvents, right? And what happens is you have to take a polar molecule that just barely soluble in the mobile phase, and then you introduce it to this phase boundary where it can stick to the surface. It can stick to the surface of the silica, and the longer it stays stuck on average, the longer time it takes to flow down the column, right? And flash is used mainly for, or flash or silica-based adsorption is used mainly for highly polar molecules, and for preparative purposes often. So preparative chromatography is chromatography that's used, when you're synthesizing a significant amount of material, and you need to collect what comes off the column, right? Analytical chromatography, you just throw it away. You just want to measure it, so see how much is there, and then you're like, no, I don't care about it. I just want to know how much is there. So now partition chromatography. This is now you have to promise not to hold me exactly to this, right? But more often than not, partition chromatography is reverse phase or something similar, right? Means you've got a silica stationary phase with some molecule bound to the surface. So there's a very common example is octadecane on silica, but you can have all kinds of different molecules bound to silica, ranging from the completely nonpolar to the fairly polar. And you get into an area where it looks a lot like adsorption and stuff like that. But just in our minds, let's say if there's a bound molecular layer, let's call it partition, right? And reverse phase is normally a type of HPLC, right? And nowadays, there's also UPLC and UHPLC, which are just basically commercial trademarks for doing things better. They use higher pressure, and they use a smaller effective stationary phase, or a smaller stationary phase. Nothing effective about it. It's simply smaller. It's smaller. It's still very uniform, but the U means higher pressure, smaller stationary phase. U is ultra, but it means, higher pressure and smaller stationary phase. Okay. So, oh, by the way, I'm so sorry. I'll put these notes on the web for you. I apologize, they're not there now. Now, you could say that gas chromatography is partition. That works too, because GC also uses it actually has a polymer coating on the inside of a capillary, and the polymer might be 100 nanometers thick or so, but it's a uniform polymer that hopefully stays stuck to the stationary phase. So there's also ion exchange, right? And so if you ever have like an ionic compound and you need to separate it, it's almost per force that you need to use an ion exchange method. And there's an easy way to think about it. And it's basically about the equilibrium constant for the association of the anion and its counterion. So in this example here, we have solution phase anions and bound cations, right? So the bound cations are typically quaternary ammonium groups, and the mobile anions are normally, and the mobile anions could be anything, right? And depending on the solvent, there can be a different association constant on average between the anions and these bound quaternary ammonium cations, right? And so this is referred to as anion exchange, right? Because in an ion exchange chromatography setup, there will always be a buffer of cations and anions running through the column. And the anions that are in the majority in the mobile phase here, they will be competing for these cationic sites, right? These quaternary ammonium sites. But there'll also be solute or analyte anions, right? Because in this case, the anion or the analyte is an anion. And so the anion can bind to the quaternary ammonium sites, and the relative strength of that binding interaction will determine the rate of migration of that anion through the column. And I have no doubt that this is a fascinating physical chemical situation, right? Because you have a limited number of binding sites, and you have a majority of anions, and you have different solute cations running through there, etc. But in essence, there's simply, you can think of it, you can boil it down to sort of a Ka between the anion and the cation there. There's a dissociation constant that determines the elution rate of a given anion down that column. So hopefully that helps, and it kind of divides the world of chromatography up a little bit, because you can have a lot of what we talk about in lab, we do neutrals, or we try to do neutrals, we do caffeine and benzoic acid, and we dissolve them mostly in water and partition them into octadecane. And that's sort of how our separation works. And but there's other sort of niche kind of weird worlds that exist in chromatography, right? And we're all, there's no, we like to put it in these global, like we can separate under that, but really we just separate what we can, the way we can, and there's a lot of really cool technology, but it basically boils down to phenomenology. Like somebody put some goo together and ran some liquid through it, and oh my gosh, look, that came out first. Let's make a separation method based on this, So it's sort of like, it's all somewhat accidental. Casey fell off screen, so I have to get Casey back.
I'm here.
Good, thank you. You and Cindy are the only people with the courtesy and good sense to turn on your cameras so that I know that someone is listening. Because if I don't know anyone's listening, I'm going to go off the rails. I'm going to get crazy. And don't use that as a reason to turn off your camera. Let's see here. What it's saying in the chat. Fook says he's here. Gianluca says same. And Fook emphasizes that
Hello.
not only is
Hello.
hello,
Hello.
hello, hello,
My microphone was
hello,
dead.
hello.
Now it's alive. I'm here. My camera broke
All right.
this week. So I
Oh,
have to get
no
it.
kidding. No kidding. Your camera broke. I bet you a wire broke.
It's possible. I don't know.
Yeah, because the stupid solid state cameras in there, they never break.
Yeah, I don't know. I open and close my
But
laptop a lot, and it's like on the top edge. So I don't know.
oh, it's on the top bezel. Oh, right. You know, half the time it's stupid software.
Yeah, I don't know. I've tried a couple things to fix it, but I just need to get an external camera. And I just haven't.
You know, so heaven forbid, but if you ever want to do a lot of zooming, there's nothing beats an SLR, a DSLR for doing this because they have really big chips and they have a narrower depth of field. So you can, if you're clever, I'm not, I'm not clever enough, obvious, but if you're clever, you can get yourself in focus and everything else out of focus. Probably I need to stop it down or something, but I just found that I have to teach a class online this summer and I'm going to be literally boring the crap out of high schoolers for 3 hours a day, every day for a month. Can you believe that? How are they going to survive? So I got this stupid better camera. I don't know if that's going to help. But anyway, I'm trying to think up good stuff for us to do. We're going to start with Mossbauer spectroscopy.
You think you're crazy?
Yeah.
I wanna go become a teacher of high school students. So who's really the crazy one?
Well,
You or me?
yeah. Well, I respect that. But the thing that I'm afraid of, Jonathan, is it's the online part of it. Because when you're present with students, I mean, you just kind of have to stay one lecture ahead. You know? Yeah, good luck to you. Good luck to you, Jonathan. And so good. The camera quality is coming out good. I like that. Thank you. But oh whoa, what is going on here? But yeah, it's just the online part of it. It freaks me out. I don't know how they're going to do it, but I salute you, and that's awesome. I'm glad you're going to be a teacher, and I know you're going to be a good teacher. So that's super cool. So basically, I better get back on track here. So one of the other ways you can do this is by size exclusion, and anybody who makes polymers or larger molecules will need a size exclusion column, and generally, size exclusion it's basically just goo. It's just goo, and it's like they make goo particles, and they're all swollen with solvent, and they flow them into a column, and they pack them in there, and then you just put your molecules through goo, and the goo will entrain the smaller molecules, but the larger stuff goes through, and so you get this reverse molecular weight thing where the large molecular weights come out first and then the small ones come out, and it's pretty weird. So size exclusion, aka gel filtration or gel permeation. And people in the know around here anyway, they just call it GPC. GPC. It's like you can ask Dr. Samako or Dr. Radlauer, hey, how's the new GPC? Ask them that, because they got an MRI grant to purchase a GPC, and they got anyway. So you get the idea there. That's another way to do it. And then there's affinity, right? And this is a biochem tool. It's not really chromatography. It's just, you could just do it on a bed. You just need a lot of surface area, and it's 99% of the time it's antibody antigen. And like the thing that you're trying to separate from everything else, just one analyte, right? Typically just a single analyte, right? And it's a chromatography to which we owe everything to rabbits, right? This should be called rabbit chromatography, because rabbits gave their all for affinity chromatography. And every time someone comes up with a new kind of affinity chromatography, they have to do horrible things to more rabbits, right? So one of our favorite affinity types of, it's basically, it's a related assay. It's called ELISA. But ELISA is used for pregnancy tests and PSA tests and other tests for identifiable antigens for example, in the human body. And the way that they'll do that is that they'll get a rabbit and they'll shoot it up with the antigen, right? The PSA or the human gonadotropin, I think is what the pregnancy test measures, or whatever they're looking for. They'll shoot up a rabbit, and then they'll get that rabbit to express antibodies for it. Then they'll get those white cells and they'll clone them, and they'll make a ton of the antibody for the antigen, right? And so once you have a bunch of antibody, right, then you can work with it, and you can find an attachment point and tie it down to a surface. And this is sort of organic stuff, organic chemistry, right? And they'll tie it down to the surface, and then you just expose that modified stationary phase to a solution that contains the antigen, right? So you've got antibodies that are all covalently bound to the stationary phase, and then you expose that to the antigen, and the antigen antibody, that binding interaction should be strong enough that you can then wash all the other molecules right out of that system, and then you have purified the antigen, right? Now you never have enough to do anything with except analyze it. You can answer the question, is it there, right? Or you could elute it. You can salt it out, where you increase the ionic strength of the eluent, and then that will break the hydrogen bonding type interactions that often tie these antibody antigen pairs together, and then you can elute the the antigen. And so, it's not really chromatography. It's because it's only directed at a single analyte. But it's in here, right? So let's look at some of the basics of chromatography. So a chromatogram is a graph that shows the detector response as a function of time. And the retention time, or TR, is the time between injection and detection, right? And then, so in this case, they have detector response in time, and then they have methane, octane, unknown, and nonane, right? And methane they're using really as a marker for what's called the dead time. And the dead time is the time that it takes for an unretained analyte to get through the column. And so dead time in HPLC, you might mark it with water, because water is completely unretained. It just goes right on through and then blip. It doesn't retain at all. And same here with methane, because methane is a gas, whatever, it barely retains it all, right? And so you measure T prime, right? There's TR and T prime R, and TM TM is the mobile phase transit time, so TM. I call it dead time sometimes, but TM, right? So TM is, or T prime is TR minus TM. So anyhow, that's how you define them. And then the linear velocity is L over TM. That's for the mobile phase. And then anyway, you got the linear flow rate. I don't care about that. Nobody cares about that. Sorry, oops. See, there's that. There's that. So retention volume, nobody cares about that. Then there's alpha here, which is alpha is the relative T prime values. And it's separation factor. And it is also happens to be equal to the ratio of the partition coefficients K. So let's just look at this more carefully. The retention factor K here, it's actually related to a partition coefficient here, but we'll get to that. It's just the ratio of the T primes. And the you can simply measure it as T prime R over TM is an individual K value, right? And also there's a volume relationship, but nobody cares about that. So, here's an example of how to calculate a T prime. Whoopie-doo, you can calculate T prime. Yay, who cares? And then you can do it for benzene and toluene, things like that, right? Now, so the idea here is that there is an equilibrium constant behind K. You find this phenomenological thing K prime, and then a sort of more physical thing, which is the partition coefficient, capital K, right? Little k versus capital K, right? And so the partition coefficient capital K is equal to the concentration of analyte in the stationary phase divided by the concentration of analyte in the mobile phase, right? And so you can relate that to little k by throwing in the volumes, right? And then relating the volume flow rates to the times, right? So a given K is T prime over Tm. It's also equal to K, capital K, times Vs over Vm. Now, that's as far as anybody ever takes it. Trust me, nobody gives a crap about the magnitude of capital K. All we care is that capital K is formally related to little k. Little k you get from a chromatogram. Capital K you can calculate if you know these ambiguous nonsense Vs and Vm. So we don't often calculate capital K, right? But little k is related to this thermodynamic thing, and it's very easily gotten by T prime over Tm. Yay. That's all we got to say about that. Little k and capital K are related, and they're all both equal to T prime over Tm. Alpha is a separation factor, and it's the ratio of the T primes. It's the ratio of the Ks and the ratio of the capital Ks. So there's a little game you can play with K and alpha, right? K refers to a specific peak, where alpha refers to any pair of peaks here. So, here's an example of how to do that stupid kind of calculation, right? And if you want to do the stupid volume calculation, you can. I haven't assigned homework on this yet because I'm going to sort out a lot of the niggly, detaily stuff that nobody ever uses, and I'm going to sort it down. Even if it's 2 problems, we're just going to do problems that matter, I hope.
Are you going to do those problems first so you
Okay.
don't surprise us with the
hell
crazy,
no.
awful problem that, but it looked easy?
Oh yeah, no, sorry, I'm not going to do that. No. I will look at them carefully enough that I know. I probably am not going to do them. That's a lot to ask. Damn it. I promise though, no surprises. I promise, no surprises. That's a fair request, and I'm going to give you as fair an answer as I can. So I will look at them very carefully, and I haven't assigned them yet, partly for that reason. So. So maybe I will do them. Maybe I will do them first. So so here's another volume one that nobody ever does. And then here's just another stupid, calculation of K, right? But so here's an interesting one. These are here's some prep HPLC columns, and I do not know what year this was taken in, but I'm judging from the pants, the very long pockets, and there's kind of high and no belt on the pants, that this could be somewhere around 1970, right? So I don't think this is a particularly modern example of a preparative HPLC column. I mean, I'm sure he's a nice guy and everything, but he's definitely a nerd. So but this type of column is not unheard of, right? It's basically just see a big old huge packed column. And if you have a really challenging pharmaceutical preparation and you have to do preparative HPLC, it's doubtful that that drug is going to get to market. But if it does, there will be technicians such as these, and they'll have huge HPLC columns. They're very fat, and they'll put in 100 milligrams or 250 milligrams at a time, maybe a gram at a time, and they'll separate them on a surface like this, and it's all proportional to R squared. So anyhow, so the volume is proportional to the square of the radius. So anywho, that's how that's done. And now here is a weird one. And just so you know that it can be done, you know, this is the column diameter, you know, surface area, meter squared per gram. There's the column length. There's the alpha value that your sample and its nearest interferent produce. You know, the alpha is the ratio of the K prime values. And so you can, this is an engineering type of a thing here. You can calculate a maximum sample injection here, but it's like, unfortunately, that is pretty small here, but sigma G can be, I don't know, many meters squared per gram. I don't know. Anyway, just to know you can do that, but I don't care. You know, it's not a chemistry thing. That's a chemical engineering thing. So, all right. So efficiency of separation, something we'll go into a little bit here. For a peak of height h, if you go to half h, you can compute the width at half height. This is one of the few very good ways to characterize the width of a chromatographic peak. It's the width at half height. Because doing this extrapolation to the baseline extrapolation is not easy. But the width at half height is normally something you can get, right? And the width at half height is equal to 2.35 sigma, assuming it's a Gaussian. They're never Gaussian, but they're close enough, right? And so this is a way to characterize the width of a peak. It can be done, right? Once you have that width at half height, you can define the resolution between two peaks, right? This weird thing here is the combination of two, or it's the sum of two Gaussian peaks separated by 2 sigma, right? And this here is defined as a resolution of 0.5, meaning unresolved. You can't really do much with a resolution of 0.5 unless you're trying to separate isotopes of uranium-238 and 235. In which case, you got to use a very poor resolution and do it a million times. But for normal chemistry, you want a resolution of at least like 6 sigma, right? You need to get the baselines resolved. So you know, so a baseline resolution of greater than 1.5 is where the distance between the peaks is greater than 1.5 times the width at half height. And that is typically when you say something is baseline resolved. Okay. There's some examples of baseline resolution. And then now let's talk about broadening. So this is the last topic that we'll discuss in chromatography in general. And it's fairly straightforward. And it just has to do with the idea that as solutes travel through a column, they spread, right? So from the start of an injection, where in theory you could have a fairly compact band, right? And there's a couple of things about this, right? That at this point, you're assuming that it's highly soluble, and all the concentration is all of the molecules are in a very narrow band of solvent that's moving through the column, right? And so this is probably unrealistically narrow. Like even when if you recall, maybe when we did the HPLC, there's a sort of and that's when the injection happens. And during that period of time, the needle is going forward and the solute is going into this flow system, right? And it's flowing down a tube to the stationary phase. Now, when it hits the stationary phase, it'll tend to bunch up a little bit because there's some retention and some slowing of the flow velocity, right? And ideally, it'll start as a very narrow band, right? And then as that solute band progresses down the column, the peak in concentration will come down and the sides will increase, right? So it gets broader. So as the solute goes through, the peak profile that it produces at a detector downstream becomes broader. And there are, what we're going to talk about next are the contributions to that broadening. What are the broadening mechanisms, right? And the first one is referred to as longitudinal diffusion, right? And we say longitudinal because only diffusion in one of three dimensions matters, right? There's like along the column, up and down, and side to side, and the only one that matters to us is along the column. So that's the longitudinal dimension of the column, and so that is the one that matters in terms of chromatography. So so for example, this is a water droplet, and this is an image of the trajectory of a 290 nanometer diameter fluorescent bead in a 20 micron diameter water drop at 155 millisecond intervals. And so basically you can plot the location of the stupid bead here in the drop. And the idea is that after each step, there's a certain amount of distance that it travels in any dimension in X or Y here. And if you plot those out, they will develop a Gaussian histogram. It looks like a slightly flattened Gaussian actually, but this diffusion is one source of band broadening in a chromatographic setting, right? There's no real doubt about this, right? And the diffusion coefficient is simply a statement of the net flux being proportional to a concentration gradient and a proportionality D. And the only thing that, the only misconception that I would like to clear up about this is that this is a purely random thing, right? There's no, when you have a concentrated region and a dilute region next to one another, there will be a net flux from the concentrated to the dilute, right? So the net flux from the concentrated to the dilute can be calculated using a linear step like this. J is d dc by dx. And it's just a random thing because there will always be flux in and flux out. But this should be called really the net flux. Moles per square meter per second, for example. Okay. And then the diffusion coefficient is equal to kT over 6 pi eta r, where eta is the viscosity and r is the radius of the particle. And you know, I don't really know why they throw this in here, but because, you know, it's just a physical chemical connection between D and other factors, but we don't really care so much about like what the underpinning of D is, right? But diffusion contributes to peak width. If you throw some of those constants in here, it's proportional to e to the minus x squared over D, right? So sigma is equal to root 2 dt. So so if the elution time t increases by a factor of 2, the bandwidth will, I'm sorry, if the elution time increases by a factor of 4, the band will broaden by a factor of 2, right? So this is where to think about this. And this is the take-home, the single take-home message about diffusional broadening of peaks, is that they only scale with the square root of the time or the distance or the column length or whatever it is that increases the amount of time to elute a given species. So it's a sort of a forgiving band broadening term, right? And here's some diffusion coefficients. That's really interesting. Yeah. 10 to the minus 9 square meters per second. But anyway, none of these matter. It doesn't friggin' matter what the magnitude of the diffusion coefficient is. I don't care if you know. You know, I despise sweet drinks, but I ordered this online and I got to Pete's and there it was. And I was like, oh, do I complain and be late to later to class, or do I just eat it? So I just ate it and it's kind of horrible, but I'm drinking it anyway. Because I don't want to be late for you guys. Later. Okay. So, you know, after all this nonsense about the width of a peak being proportional to basically to x, or to 1 over x, right? Well, anyway, there's a weird connection here. I don't want to get lost in it, right? And the plate height here is, it's just something to get used to, right? It's equal to sigma squared over x. X is the distance the band travels, right? And sigma squared is the squared this half width at half height, right? So this value, sigma squared over x, you can just combine those two terms into h, right? You can just do this, right? It does not mean anything. It's just a stupid friggin' number that they use in chromatography, right? So you kind of gotta, if you're prone to having sticks up your tail, like me, you gotta let it go. So a small plate height, right, means a better separation, right? So a small h value means sigma is small relative to h. And you know, so a small plate height is good. It's more typically that someone will say n, the number of plates that you can generate with your column, right? And the number of plates is generally specific to a particular peak, where you take the TR for that peak and the W of that peak, right? And, I don't know why everything's squared here. It's just weird, right? But this is the operative form of it, right? Because W you can measure from your chromatogram, and TR you can measure from your chromatogram. So this N is something you can just get from a chromatogram, and that is fine. None of these other things matter at all, except this one. And N is a dimensionless metric of the separating power of your column, right? And you can just do the stupid calculation. For a given TS, you can find the plate height. Whoopie doo, it's it's half a millimeter, right? And so sometimes there's asymmetric peaks, not asymmetric, non-symmetric, not anti, but and then there'll be a different kind of width measured either way. And I don't know about this shit. I don't care. I really don't care about this. Don't worry about it. Promise no questions on this. Now here is a case where there will be a question or two, and this is resolution. And the resolution alpha, or I guess you could say the resolution R here is, root n over 4 times alpha minus 1 over alpha times right? It's proportional square root of n. So let's look at what alpha means here. So this is kind of cool, huh? Check this out. So they have here's maltotriose and cellotriose, right? And you can tell that there's a different stereochemistry at this ether bond that links the two sugars, right? And I don't know if you guys know about the story about cellulose versus carbohydrates, but the cellulose for 99% of all critters is completely indigestible. You cannot digest it. But normal carbohydrates like maltotriose and whatever, they're very digestible. This is actually a pretty labile bond here. So the carbohydrates turn into simple sugars once they hit your gut. Even in the mouth they start, because you have amylases in your saliva, which start to attack these bonds, right? But somehow, just the stereochemistry of this thing turns, like starch into wood. That's the way to express that difference, right? And so now it's odd here, but for this trimer, there's even though if you were to break it down, you could totally separate them, right? You could totally take this mixture and put it in with some amylase and break this down completely and leave this completely whole, and then you could separate them, right? Then you get 3 times the size of peak here than you would here, right? Where you get 2 peaks, right? 1, 2, and then this dimer here, but this would not break down at all, right? In this case, what they did was they cycled it through a GC column, I think, or maybe an LC column, and they cycled it a bunch of times, or here 16 times until they got baseline separation, right? And at 1, they've got a little bit of separation too, and then 16, they've got baseline separation. And it's an interesting sort of example of one thing about chromatography, is that in order to separate things, you have to retain them. So, so that is the lesson from this here, right? Plus the interesting sort of aside on how cellulose and carbohydrates differ. Just that stupid stereochemistry. So now, what things that affect resolution, you know, are basically K and then alpha, right? So if you have poorly separated peaks, you can increase both values of K, right? You can simply, this is what was done up here with this thing. They simply continued cycling them through the same column, right? They just increased the retention time, and that resulted in resolution eventually. A better way to do it is to somehow increase alpha. And by increasing alpha, what you do is you change the retention of one peak relative to the other, right? And then lastly, what you can do to improve a separation is increase N. N is the number of theoretical plates generated by the column. So I'm going to hover here on this one for just a minute, and we'll probably finish up with this guy here. But how, for example, could you increase K? What could you physically do to increase K? Any thoughts on that? Okay, let me start you off then. To increase K, you simply increase the length of the column, right? And so you retain it longer, and then the longer you retain it, the longer time you have for the bits to separate, right? I mean, obviously, if you have very, very narrow column, nothing's going to separate, right? Okay, now, here's a hard one. How do you increase alpha? So here, the first peak is at the same position, but the second peak has moved. And how might you increase alpha? Just spitball something. So with HPLC, right, how can you change the selectivity of the separation? Let's say that caffeine and benzoic acid were coming out as one peak or one unresolved pair of peaks, right? How can we get them to move apart? And there's so many degrees of freedom. What's one thing we
Change
could
the mobile
change?
phase.
We could change the mobile
mobile
phase. Exactly right. If we can change the mobile phase, then we can also change the, Cindy? The mobile versus the stationary.
Stationary.
Exactly. Good. I love it. So you change the mobile phase, change the stationary phase. You can change the pH of the mobile phase. And that's about it, I think, right? Because changing the mobile phase and stationary phase, that could mean a lot of different things, right? But increasing alpha, alpha is a very specific thing, and that's changing the relative affinity of the two solutes for the stationary phase relative to the mobile phase, right? That's how you're going to change alpha. And that is this is really the most fruitful way to approach any kind of separation, right? I mean, once you have a given K, if you try to just increase K arbitrarily, it just takes forever, and you're going to run out of column length and stuff. So this is not common, right? But to increase alpha, you can play with this, you can tune the solvent composition. What I did for caffeine and benzoic acid was I just changed from, I started out at 60-40 water methanol. Then I just added 5% acetonitrile to that until I got to 60-40 water acetonitrile. And the sweet spot in that was 60-30-10. I just took that combination, and that worked for separating caffeine and benzoic acid in Coke. So I presume there's going to be water in one modifier, and then I took 40% methanol, then 35 methanol, 5 aceto, 30 methanol, 10 aceto, 25 methanol, I don't know, I forget, 15 aceto, something like that, right? And I kept going in that direction, right? And then that changed K, and then there was a sweet spot there at 60-30-10, I think. That's how I remember it anyway. So now, and that was all in the area of increasing alpha, the alpha value. Now, one thing that is done instrumentally, like this is the throw money at it approach, and it's not, I'm not trying to denigrate it, but it's a good way and it works. But this is plate height were made smaller, right? This is the UPLC approach, and this is this last one, and that's just to make the peaks come out narrower for a given pair. So that's where we should leave it off today, and then we can look at the summary equations and whatnot. I can go through these, and we'll scratch a few of them out, that don't matter. All right. And so that's good for today. I promise I'll get some homework out today or tomorrow, and things that I've worked through, I promise. And then I will see everybody again on Thursday. Okay. Bye.
Thank you.
Any questions or anything? No, never any questions. Okay. Bye-bye.